In this midterm demo, our team will be going through a series of tests. First, we will be conducting a power budget analysis of the ADCS in order to determine an operational life expectancy of the system. Second, we will perform a test of each of the axial motors, one at a time. Third, we will run a test of each of the axial motors running in parallel with each other. Fourth, we will conduct a rotational test by ramping up the speed of the z-axis motor and witnessing its effect on the TubeSat. And finally, we will demonstrate the stabilization capabilities of the ADCS on the TubeSat. This test will only be performed about the z-axis and will be a close representation of how the system will act in the space environment on any given axis. To the right is a table that outlines some key specifications we intend to showcase in this project. These specifications are maximum current draw, RPM range of the motor, motor frequency range, and axial stability of the system. Some uses for an ADCS that are worthy to note are establishing pointing accuracy for directional antennas and achieving the highest possible gain, Earth observation, and stability for sensitive onboard experiments. Here we begin our power budget analysis of the ADCS. To perform this analysis, we first began by charging all 3 lithium-ion batteries to full charge, which takes about 20 hours. Then we connect the ADCS board to the main board and upload the following code seen on the left to the processor. This code begins by setting the PWM frequency of the TCC-R5B register to about 31 kHz. This is required by the motor controller in order to operate. Then we set the corresponding PWM pins for motors X, Y, and Z to the output state and initialize them to 0 for best practice. The following loop starts off by setting the motors at its lowest speed in order to properly transition from the open loop to closed loop stage. We then quickly ramp the duty cycle to 135, which happens to correlate to about 7,500 RPM on the motor. I will discuss how I know this correlation in the next slide. 7,500 RPM was chosen because it's about half the maximum speed of the motor, and the team wanted to avoid any unnecessary wear and tear on the motors by operating them at maximum speed for many hours. Moving forward, we note that 7,500 RPM will result in a current draw of 320 milliamps per motor according to our motor manufacturer. The video on the right shows all 3 motors operating at 7,500 RPM. 2 of the motor frequency feedback pins are connected to 2 of the channels on the digital oscilloscope. A third feedback pin would have been connected if we had an extra channel, but for the purposes of this demo, it is not necessary. The frequency of the signal driving the motors can be seen on the screen. The motors were driven until the frequency driving the motors dropped off due to a depletion in the lithium-ion batteries. Starting with the graph on the left, we can see a correlation between motor frequency and set PWM. PWM values lie on the x-axis of the graph, while corresponding motor frequency values lie on the y-axis. These values were found by developing code that slowly ramps the PWM signal from 25 to 255. Before the code is run, the motor frequency feedback pin is connected to the digital oscilloscope. Once the sequence has begun, corresponding frequency values are logged in Excel spreadsheets through each transition in PWM value. Taking this analysis one step further, we can calculate corresponding RPM by using an equation provided to us by the motor controller manufacturer. According to the datasheet, the motor frequency can be multiplied by 60 in order to find RPM. With this information, we were able to develop the graph on the right. Now we have reached the end of our power budget analysis. In this table, we have recorded the following parameters to be true in our test. Operating motor voltage was 5 volts. Motor speed set was 7,500 RPM. All 3 motors were running in this test. Each motor drew about 320 milliamps. Lifespan of ADCS during the test was 7.5 hours. Final energy capacity is 7,200 milliamp hours, and at 5 volt operating voltage, we have a power capacity of 36,000 milliwatt hours.
In this video, we will demonstrate the testing of the different three motors on the different three axes. We are testing the motors on the three axes because we want to ensure that the motor operates individually on each axis, since in space we will not know on which axis the satellite will be tumbling. Right now from the video we can see that the motor on the x-axis is spinning clockwise trying to achieve the maximum RPM, which is 15,000. Our individual test starts from the x-axis to y-axis and it will end in the z-axis. As shown in the problem from the code, we can control the speed and the direction of each motor individually by the digital right and analog right. If the digital right is set to high, that means that the motor will be spinning clockwise, and if it's set to low, that means the motor will be spinning counterclockwise. Also, we control the speed of the motor by analog right, which is the PWM signal. As shown right now in the video, that the z-axis is spinning clockwise trying to achieve the maximum RPM. Once it achieves the maximum RPM, the motor gonna shut down for 10 seconds. After a 10 seconds delay, the motor will start spinning again counterclockwise trying to achieve the same maximum RPM, which is 15,000. For our individual test case, we have tested the three different motors on the three different axes, with a minimum speed of 990 RPM to a maximum speed of 15,000 RPM. For the demonstration of our project, we have shown the z-axis motor spinning clockwise and counterclockwise. But we also tested the other two axes, which are x and y. And we have also obtained the maximum RPM and all the test cases were successful.
Our simultaneous test consists of all three reaction wheels running at the same time. For our simultaneous test, we wanted to verify that a reaction wheel could do the following. First, we wanted to operate at the same frequencies and therefore RPMs that individually they could operate at. This is important not in the overall effect of our system working or not working, but it could have influenced the way we code our ADCS reaction if we were limited during the operation of multiple wheels. For example, if we had seen a drop in performance between a single wheel accelerating or decelerating and multiple wheels accelerating and decelerating, we would have preferred to use a code that would maximize the lifespan of the system, so it would have been likely that we program only one wheel accelerating or decelerating at a time. Second, we wanted to make sure that there were no gaps in the speed at which the reaction wheels operate. So as you can see in the code, we stepped up and down by increments of 1, as well as changed direction to test all possible scenarios. Finally, we wanted to make sure that our motors were completely independent, so we had them stop at different speeds during ramp up and ramp down to verify that aspect. So I would like to point something out. So in our individual tests, we wanted to, but initially could not test multiple wheels while connected directly to the USB adapter due to a limit we had on the current that was being pulled. This meant that we had to use the battery system and upload the code. This would have proved challenging if we had delayed the purchasing of any parts that we needed for the finalized overall design, but fortunately we had finished our design portion 2 months early. So this is a good summary of our simultaneous test results. On this checklist you can see that the minimum motor speed, which is 990 RPM motor output, was verified, which meant it was the same as the individual test data. The same thing for the maximum motor speed at 15,054 RPM. Another test we wanted to do was a simultaneous motor test where all the motors clockwise and counterclockwise ramped up and down at the same time, and that we could also operate them at different speeds without an issue. Our system rotational test is simply put a proof of concept. We wanted to verify that our reaction wheel created enough momentum to spin the satellite. This also served as a test for our demonstration rigging to determine how to best simulate a frictionless environment. This becomes important as the fishing line creates additional forces that our wheel would have to combat against to stabilize the satellite.
The functionality of our system was tested in the ADCS reaction test. First, we want to simulate how the satellite will behave in space upon deployment without the ADCS system. This is shown in the clip on the left. As we can see, the satellite spins about the z-axis indefinitely, without anything to slow it down and eventually stop it. The clip on the right side will show us what happens when our ADCS system is implemented. We can now see that the satellite no longer spins indefinitely like the one on the first clip. This is because the gyroscope detects a spin and the corresponding motor turns the reaction wheel to counteract the angular momentum. The wheel keeps spinning until the system comes to a stop, which then maintains the current RPM to prevent the system from further spinning. The following code was used to perform the ADCS reaction test. First, we declare the output pins on the Amiga 2560 and initialize the IMU, which will collect the gyroscope readings. We have a function in our code called update, which takes in the gyroscope value as a parameter. If this value is greater than 0, the speed will increase in increments of 1, otherwise it will decrease by 1. This happens on a continuous loop until the gyroscope value becomes 0, causing the motor to retain its current RPM to keep the whole system stable. We have also added a cool feature to our code where we can take the sign of the speed to determine the direction of the motor. For example, if the speed is positive, the direction that the motor will spin in will be a clockwise direction. Otherwise, if the speed value is negative, then the motor knows that it needs to spin the other way. To summarize our middle term demo, we have shown and tested 4 engineering specifications. The maximum current draw was calculated using the manufacturer datasheets, and we expect to have a full load of 1912.5 milliamps. The motor frequency ranges from 16.5 to 250.9 Hz, and we can confirm this using an oscilloscope. The motor operates on a range from 990 to 15,054 RPMs, and this can be found using the frequency obtained from the oscilloscope. We can plug that value into the RPM equation provided by the manufacturer. Finally, the last requirement proves that our system works as intended because we're looking for an axial stability of 0 degrees per second plus or minus 0.1 degrees per second. We use the IMU data in our code to determine what speed the motor needs to have to achieve stability.
Thank you. Any questions?